then I'll start this. Okay, so we are now in the exercise session concerning threads, and what we are going to do is we're using the example where we calculated pi, which was here in lecture 6, main serial, and I copied this to lecture 8 and I rename it to main threads, and so you should take a copy of this too and put it in your own folder. Yeah? So that now this year, lecture 8, we can now just go there, see that it's now only the file. It is the original serial file, and we want to change this in order to run with threads. Here do I need to have this to compile this actually with PT threads? Yeah, I think so. Okay, I can. So since we are not using MPI this time, we are going to compile with G++ instead of MPI C++. And even though there are no these threads in here, I use the what is it called? The argument p threads, and I'll compile main threads to p threads. I don't know. So just seeing that it compiles and then seeing that. Okay, we had some. We are doing again the bad thing and run it on the login node. We had some problems with the pipeline last time. We are only using very, very short calculations, so I hope nobody is going to complain. Yeah. So basically we run the serial thing, we just called it P threads. So now we want to turn this into a code that uses threads, and I encourage you to somehow follow. So you should be able, when you have this code in front of you, you can try to type together with me and hopefully actually helping me. So the first thing that we need to do, obviously, is to include the header for the threads. Include threads. So I always want to say threads, but it's thread. Okay. So this is the first thing. What is the next thing that we have to do? In order that we can use threads in the first place. Remember, threads always need functions to be called. Yeah. So we have to define somehow a function for what we want to do. Now, I remind you this. Okay, maybe we have to look again through how this thing here works. So, since we don't use a header, we declare our function here in the beginning of this. So usually this would be in a header. Yeah. Here we have the function integral. Or integral, yeah, that just integrates this part here, where we get a left boundary, a right boundary, and divisions, and then this integrates the function f, and the function f itself is defined somewhere here. Now we have several options. Ah, no, we don't. Okay, yes, we don't. So, so usually we would say, okay, the thing that we want to do is already given is given in a function, right? So we could simply tell the thread to call this function and give the appropriate boundary values here. So why wouldn't that work? There was one condition on that function that we had in the, okay, we potentially need to look in our notes. So there was one condition. Let me see where's the right okay, we have it as an example here, right? So we have this function here, which we call from the thread. And the one thing that you have to take into consideration, this function is of type void. So it has no return value. Whereas the function that we wrote here is of type double. Now we could modify this function, or, and this is the step that I suggest we do, we write a new function. Or let's say we declare a new function, and I will call this integral threads in order to know that this is for our threads. So this, I suggest, would be given the same argument. So we'll actually I could copy this. Just with one small addition, namely that it has to return its result. Yeah. So basically, we do this the same way as the MPI function is doing this. We pass a value by reference, which we call result. Okay? So we simply return the result of this. So this is our declaration, and then okay, you're following me, right? So we declare this like this, and then I suggest we go where we have this function, the other function defined, and define our void. I mean, we could define it up there, but now since we have it, since we defined this as our style, we do it down here again, integral thread integral thread. So you have to live with my dyslexia again. So I hope I wrote it the same way. I put here the same arguments, and in addition, I add here, let's see, I have a little bit of my cheat sheet. Yes, result and, no, sorry, double and result, okay? So, what is this supposed to do? It's pretty simple. It will put into result. Okay, this is basically what we call a wrapper. Yeah, so it uses the function. It just changes the outside behavior. We simply put in result the result of integral that now we call with, okay, boundary left, boundary right. Okay, I should, when I write it like this, I should also write it like this here. Boundary left, boundary right, and divisions. So, apparently I mistaped this. I wrote boundary and it should be boundary. Okay. Does this help? Yes, this helps. So, that's a pretty simple wrapper function. Okay? So, now we need this is kind of the infrastructure. Now we kind of have to get this going. So how would that happen? So here is the place where we call our integral. Yeah. So here, instead of calculating the integral, we would call these functions. We would call these threads. Okay. First and foremost, we have to make a decision on where to store our threads and how to identify how many threads. So, because this here was prepared to run with OpenMP, we have already here a few things defined, namely the number of processes. Yeah, so I would suggest that we can just, in order for not to, I mean, this may be not the very best style. Maybe we should do something like this: find and destroy. We should say number of processes should be replaced everywhere by number of threads. So that would be a little cleaner, yeah, to have the right names. Let's do this. So, okay, it has done all the replacement for us. No, okay, the number of threads, now we can here define 1, we can define different number 10. Okay, so then the next thing is here my rank, which we should potentially replace with my rank should be my thread, right? Bless you. My rank, my thread. Oh. That was not good. I replaced my rank by my threads. That I should redo this. I should replace my threads with my threads. Let's do this again. Is this actually happening everywhere? Okay, so just that we use a more appropriate nomenclature for our setup, yeah? But this has not yet changed anything. So now we one thing that we need to do here is to actually store our threads someplace. So in the other example, we used a vector. Now I suggest that because I'm giving here a static number, I can actually use a usual array, a usual C array, because this will be known, this number here will be known at compile time. Therefore, I'm just using a usual array, and maybe I'll put this here. So the array would be of type thread, and thread is in the namespace standard. This is why I have to indicate that this is standard thread, and here I want to have an array of threads which I call threads. Yeah, threads array, and I give this number of threads. So since this is known at compile time, it should work. So in addition to these threads, we also need to capture our results somewhere. This means we also need to have an array of results. Meaning we put here double results, which again is an array, which we have to go through an array of the number of threads. Okay, so now we have an array of threads and we have an array of our results. Okay. So we know how to start and we know where to store. Now, this is so this is the part that we had prepared for MPI. Yeah? So there's this global interval, and then there will be a local interval. So the length of this interval, and then a local starting point that is related to my thread, and a local endpoint that is also related to my thread through being related to local A, right? So then this, since we are not in MPI, we have to decide on what thread we are in between here, and I suggest therefore we split up this position here, and from here we make a loop. We make here a loop over our threads for int. Oh no, we've already indicated my thread, so I say my thread here is starting from 0, and this goes through obviously my thread smaller or equal smaller, yeah, smaller than, what have we called it? No, sorry, number of threads, and then my thread plus. Okay, so it's a little bit inconsistent to call this my thread, I find, when I look at this way, but let's stick with this. So, okay, I open the scope, and I will finish the scope here, well, I'll take out this line. Yeah. So what we do for each thread that we are going to start is that we calculate its local domain. And then instead of doing this here, we will start or generate, is it called? Yes. So we'll take threads in this array according to my thread, and now we have to start this. So this is by setting this equal to standard. Now we have to make the start standard threads. So this is actually, okay, so this is maybe I'm again in a bad style. So this is not the variable thread, but it's the function that starts the thread. Yeah? So this is now called with the function as the first argument. Integral. Oh my God, what did I do? I just see that I must have so this is the good thing from this. So integral. Okay, so I have. Okay, we have to go up. I must have misspelled this somewhere. Integral threads. Okay. Let's do this again. Integral threads. Okay, so here, this L doesn't belong here. Okay, good. Integral thread. So now there's only one left. Now, in addition to this, we give the arguments to this function. And here I kind of have a little bit to look into my cheat sheet. Yes, so we can, so the first variables that we have here is we have to see what variables do we take. We take the left boundary and the right boundary, the divisions and the result. Yeah? And left boundary, right boundary, and divisions, they can all be passed by value. So we're going to pass these by value. So this is local, okay, again, that I don't make this mistake. Is the local, yes. Local A, local B, so upper and lower bounds. Then the divisions, okay, I'm a little bit, because we put them in a loop, I'm not sure that we should call them consts. I think they should be not const in this context, yeah? So the divisions is local interval width. Local interval width. Local number of interval, no, so this is, okay, so, right, the second number is the number of how many intervals we have in a local integral. So this is the local number of okay, you know, I'm completely stupid. I should just use what is written here, right? Because we are replacing this. Okay, so local number of intervals. So, and now the important thing is that we have to get the result back, and for this we have to go through this a little bit strange nomenclature, that we have to generate a reference to result, so to where we want to write our results, and our results are written into an array, because each of them has to write their result in a different place, otherwise they would overwrite them, each other, right? So therefore we make this reference to the result, and this again has to be at the position my thread. Okay, so brackets and semicolon. Okay, now we have called our threads. So we go through this loop. I don't know whether I can I get somehow rid of this completely? Yes. So we go through our loop. The loop ends here, and we have generated our threads. Then, because we are generating these threads, here actually we wanted to compute our final result, but obviously we have to wait until the result has been calculated. Therefore, in this position now we have to make the joining. Yeah. Okay, I don't know. Maybe I should involve you more. Yeah. So what you tell me what we do in order to get this joined again. Okay, maybe yes. So we ask for joinables. Yeah. Okay. Let's go back to our example here. I mean, usually they are joinable. We could also not ask for this, but it's better style to do it. So if they are joinable, we join. Now here we had two threads, yeah, but now we have an unknown number of threads that are in an array. So what do we need to do to join all of them? A loop, yes. So how does this loop look like? Yeah, it would be, basically it would be the same as this one, right? So I would just copy this here, and now we do the join. Okay, we do it, yes, let's do it with asking whether it's joinable. So we have this threads. So, and here again we go through my threads. If this is joinable, if it's joinable, then we'll join. If it's joinable, then we'll join it. So this is threads my threads dot join. Okay, so brackets close. So now we have all of them. Okay, and now we would usually add up the results. Which, okay, now we have the results in an array, and this array still has to be, added up. Yeah. So this unfortunately has to be done by the master thread. Otherwise, I mean, this is now the same thing as we had with master slave. So the master has to add things up. So again, several ways to do it. Any suggestions how we would do it? Okay, it doesn't need to be the best solution. Just give me a solution, and then we discuss whether this is a good solution. So my appointment started 3 minutes ago. I told them I will be late. Well, yeah, we have to add all of them, right? So that basically means we have to go through a loop. Yeah, but I mean, we already have a loop. So usually we want to have as few loops as possible, or sometimes not, I don't know. So obviously it doesn't make sense to have these loops even though they go over the same thing, but still we cannot use the same loop here and there. Because here we start them and here we stop them. Otherwise, so what would happen if we put this into this loop here in order to save one loop? I just say, okay, there's a loop and the same loop again, why don't I put this up here? It will finish. Yes. But what would it do? I mean, it would be very stupid because we start a thread, then we wait till the thread is done, then we start the next thread and wait till the next thread is done. Yeah? Do you see this? Or should we try it out? So here we start threads. Yeah? So when we put this right after starting the thread, then the thread is started and we wait until the thread is finished. And then we start the next thread. So we have serialized our work. Yeah? So this is why we have to start all of them in the loop and then we have to stop all of them in the loop. And these two loops must not be together. So now, in principle, because we don't have a local integral, so this will not work. But now we want to put the result, so we have to sum up the result from this here. And I believe we can also do this inside the same loop. Result is to the result is added the results of my thread. So why is this permissible? Why I believe it is permissible? Maybe I'm making a mistake. Yeah. So maybe some of these threads have not yet finished, right? So, however, because we go through the one, the threads number n, my threads, yeah, this must have finished when we arrive here, because this was the last one that we have been checking, yeah. So basically, when we put it here, and the last 5 threads takes longer, then we've already started with adding up. So maybe it's even better to put this here. But the important thing is that we have to make clear that the result from the threads that we are picking up here has already finished, and this is something that we checked here, because here's the barrier for my threads. So when this goes beyond this barrier, my threads, the result of my thread can be used. Okay. I kind of have the impression that this is what we need. Okay? Let's save this. And okay, now we need to have this compiled with p threads minus threads and so on. Let's see whether this compiles. It actually compiles. Now let us remember here that the previous version took 4.4 seconds. Now we try to run this with 10 threads apparently and see what happens. Oh, it does something. That's okay. Okay, I guess I know why. Yes, you know, this, so this here, so there's no writing out because there was this, okay, where we replaced my thread and with my thread 0. So this kind of doesn't make any sense anymore, yeah, because we only have one process doing things. So I have to, you know, delete this. So, you know, this was only the master process was going to write out things. Now we are the master process, and the problem why this didn't work anymore was because I misused this for counting this up, and so this actually would now be 10, and so would never enter here. So I have to do this again, and then run it again, and still it doesn't write anything out, because I have not saved it. My favorite mistake. So, okay, so previously we had 4.4 seconds, and with using the threads, with using 10 threads, we reduced this to 0. Okay, so we see it is not 10 times as fast, yeah? Because 10 times as fast would be 0.44. Yeah, so again, what we can try is when we put this to one thread, so then everything would be done in one thread. So I would expect this to be slower than the serial version. It was just a little bit faster than the serial version. And now then, yeah. Okay, so coincident, I would say. Okay, so let me now close the recording of this.